Hi everybody. Today we're going to talk about Newton's first law, and when we say Newton, we're talking Isaac Newton. He lived in England in the late 1600s, did a lot of work with physics and math and things like that, but he came up with 3 laws that talk about forces, and we still use them today. So Newton's first law, which we abbreviate N1L, goes like this. I'm sure you've heard at least part of it before. An object at rest stays at rest, and an object in motion stays in motion, and here's the part you may not have heard before, at a constant velocity, unless there is an unbalanced or net force. So let's break that down a little bit. An object at rest will stay at rest if the forces are balanced. So let's just talk about the first part here. An object at rest stays at rest. So if you've got an object here that's not moving, it's going to continue not moving until forces start pushing it around. So at rest stays at rest until forces are unbalanced. Right now, if we were to draw the forces acting on this box, there would be 2 of them. Force of gravity pulling down, and the normal force from the ground pushing up. And those 2 forces are equal and opposite. The fact that they are equal, we could use little tick marks that you might have used in math class before to show that they are the same. That means these forces are balanced and the object does not accelerate, it stays put. Now let's talk about the second part of the statement where it says an object in motion stays in motion at a constant velocity unless there's an unbalanced force. So now you've got this block that's sliding to the right. Let's say that it's on frictionless ice. That object has 2 forces pushing on it. Gravity pulling it down, the ice pushing up, that's the normal force, and that's it. There's no friction because it's sliding across frictionless ice. So since these 2 forces are balanced, this object is going to continue moving at a constant velocity. It's not going to speed up, it's not going to slow down. It's just going to keep going at the same speed it was already moving at until something stops it. Until there's some friction, until it runs into something. Something has to change in order for it to change its speed. When all of the forces are balanced on an object, we say, so balanced forces, we say the object is in equilibrium. So both of our objects we've drawn above here are in equilibrium. The forces are balanced. This means the object will not accelerate. It won't slow down, it won't speed up, it won't turn. No acceleration is going to happen when you're in equilibrium, when you have balanced forces. And when you have balanced forces, that means that something called the net force is 0. Net just means total. So if I had an object that had a force to the right that was 10 newtons and a force to the left that was 10 newtons, the net force would be 0 because you've got 10 to the right, 10 to the left. It's like tug of war. They cancel out. So this object would be in equilibrium and it wouldn't accelerate. If you have an object that has a force to the right of 10 and a force to the left of 5, or let's change it to a different number, 4 newtons, now you've got a net force of 6 newtons to the right. Net force, F with a subscript net. If, last thing here, forces on an object are not balanced, the object will accelerate. So let's add that below. Object will accelerate. And by that we mean speed up, slow down, or turn. In this case, the net force is no longer 0 if the forces are not balanced, as you can see in the example on the right. One more quick example of this unbalanced forces. Let's say we've got a force to the right of 10 newtons, force to the left of 4 newtons. And our object is already moving to the right. So these little lines show that the box is moving to the right. If I were to ask you if the object is going to speed up or slow down or go at a constant velocity, you need to look at the situation and see, all right, the forces are not balanced, so it can't go at a constant velocity. So it's either going to speed up or slow down. So if in this picture, I've got more force in the direction that it's already moving. Right? Our net force is 6 newtons to the right, the way it's already moving. Since that push is in the same direction it's already moving, our object is going to speed up. If the 6 newtons of net force was in the opposite direction of the motion, that means there's more force against the object than there is with it. That would cause it to slow down.